Take a circle on the plane and take 6 points on it, A, B, C, D, E, F. Connect A, B and D, E and mark the intersection as X. Connect B, C and E, F and mark the intersection as Y. Connect C, D and F, A and mark the intersection as Z. These newly constructed points X, Y, Z are collinear, meaning they lie on the same line. This is independent of where the points are chosen on the circle, even the order doesn't matter. Again, take points A, B, C, D, E, F on a circle and mark X, mark Y and mark Z similarly. They are on the same line again. This property is called Pascal's theorem, named after the famous mathematician Blaise Pascal. The Latin name of this theorem is Hexagramum mysticum, meaning mystical hexagram. Today, we will prove this beautiful theorem. There are different proofs using different techniques, including homothety, Menelaus theorem, cross ratio, isogonal conjugates, and Bezout's theorem, which we will choose to move forward. This theorem concerns algebraic curves and their intersections. But first, we need to understand what an algebraic curve is. Just like algebraic numbers are zeros of polynomials in one variable, algebraic curves, which we will denote with fancy letters, are the zero sets of polynomials in two variables. The degree of a curve is naturally defined as the degree of the polynomial, which is the maximum number I plus j, such that we have a term x to the power I, y to the power j with a non-zero coefficient. Now, let's look at an example. Consider the polynomial y squared minus x cubed minus 3, which is of degree 3. The graph of that curve looks like this. We will mostly rely on geometric intuition to get a grasp of Bezout's theorem. Let's see a few other curves. The unit circle x squared plus y squared minus 1 is a curve of degree 2. A line, for example y minus 2x minus 3, is a curve of degree 1. A little nuance is that we don't allow the same component to appear more than once, since that would contribute nothing to the zero set of a polynomial. For example, we won't deal with polynomials like y minus 2x minus 3 squared. However, multiplication of two different lines is perfectly fine, and indeed this is a curve of degree 2. An interesting question about curves is to count the number of intersections. For example, take two lines, y minus 2x minus 3 and 3y minus x plus 1, which are of degree 1. They intersect at one point. In place of a line, put a circle, which is of degree 2. They intersect at 2 points. It may be less than that, but 2 intersections are the most we can get. Now, in place of the other line, put this curve, y squared minus 8x cubed plus 3x minus 1 of degree 3. Now we have a curve of degree 2 and a curve of degree 3. They intersect at 6 points. Finally, take these two curves of degree 3, y minus 3x cubed plus 3x and x minus 3y cubed plus 3y. They intersect at 9 points. These intuitive examples lead us to the Bezout's theorem, which says that if we have a curve C of degree n and another curve D of degree m, then the number of intersections they have is at most n times m, which is the product of their degrees. An important note is that we require the curves not to have a common component, otherwise the theorem doesn't apply. We will now use this to prove Pascal's theorem. Let's construct the diagram of Pascal's theorem again. Define C to be the product of the lines AB, CD, and EF, which has degree 3. We will denote the degree of a curve with a subscript to the polynomial. Similarly, define D to be the product of lines BC, DE, and FA, which has also degree 3. The points that are on both curves are A, B, C, D, E, F, X, Y, Z. There are 9 of those, consistent with what the Bezout theorem tells us. And define E to be the circle. C and E intersect at A, B, C, D, E, F, again consistent with the Bezout theorem. The same goes for D and E. Now take a point G on the circle, different from other points. With the lambda defined as minus P of G over Q of G, we define a crucial curve f to be the curve P plus lambda times Q. Lambda is specifically chosen such that G lies on this curve. It has degree 3 because P and Q both have degree 3. Let's look at these 7 points A, B, C, D, E, F, G. They are all on the circle, which is of degree 2. And since f is constructed such that G is on it, and the other points are on both P and Q, these 7 points are all on the curve f as well. 7 is greater than 6, which is the product of the degrees of E and F. By Bezout's theorem, it seems impossible, but the theorem is valid only when the curves in discussion don't have a common component. Therefore, E and F must share a common component. That is, we can write polynomial S as the product of R and some other degree 1 polynomial, say T. Points x, y, z are on curve F since they are all on P and Q. However, they are not on the circle. Hence, they must all lie on the curve defined by T, which is a line since it has degree 1. And with that, we have proven Pascal's theorem. One thing you might have noticed is that, in this proof, we only used the fact that E is of degree 2, not that it is a circle. Therefore, this theorem is valid for any curve of degree 2. In fact, what we have seen so far is only a special case of Pascal's theorem, which is generally stated for any curve of degree 2. We will look at one more interesting case, where the curve we choose our points on is the product of two lines. It even has its own name, Pappus theorem. Similarly, we take points A, B, C, D, E, and F on two lines. Construct X, construct Y, and construct Z. Points X, Y, Z are on the same line again. With that, we conclude this video. Hope you enjoyed. Thank you and see you again.